So, in the test pattern generation process, the tags algorithm. So, as we have seen, like it will start with some basic pattern, and then it will go on augmenting that pattern set by doing newer and newer memory operations. So, there are this generation process of this template. So, we can divide it into two parts. One is called template generation, other is called template filtration. So, in the generation part, so if you do not put any restriction, then naturally there are so many options that this generation process becomes too costly. So, we follow some heuristics or some procedures by which we can augment these templates. So, what are the augmentations? Like given a template, so you can do one read insertion, this R insertion, that is a standalone read that we are inserting. So, this R can be inserted anywhere in the template T excepting at the beginning. So, your template T maybe we have got a single write. Okay. So, in this we can introduce a single this standalone read operation. So, like this. So, I cannot do it at the beginning because there is no point doing a read operation before doing any write operation. So, this read operation may be inserted after the write operation. So, that is one extension of the template T. Other expansion can be that we can finish after one template is over. So, we can put another template and insert R at the beginning or at the end. So, in a template element we insert R at the beginning or at the end or at the end. So, if I have got a template like some say W, as we have taken the example. So, this can be extended as WR. So, that is this reading, the difference between this one and this one is that. So, here this W is applied over all the cells first all the cells are written and then all the cells will be read, but in this case the cell that is written is read immediately and then only we can go to the writing of the next cell. So, this is the template element insertion R at the beginning or at the end. So, in the within the template, so we can introduce R at the beginning or at the end. Similarly, we can introduce a standalone W operation, so and standalone write operation. So, we have got, as we are talking, so we have got this template. So, it can be extended by another write operation. So, that way it can extend the write operation by putting another it can extend the template by putting another standalone write operation, or we can have expansion. So, this template may get expanded by putting a write at the end or putting a write at the beginning. So, at any point of time, so if you have got a set of templates, then those templates can be augmented. So, you can expand individual templates, or you can introduce new standalone operations of read and write within the template. Now, so that is the generation part. So, after generation it may so happen that you can generate some of the templates which are meaningless, like this consecutive read. So, this consecutive read we have got two successive reads. So, these are not very much useful excepting when you are trying to test say read disturb fault. So, this is not useful. Similarly, this R followed by R. So, that is standalone R followed by standalone R. So, that is also meaningless because of the same reason. And the tailing single write. So, if your template set if your template ends with a write operation at the end, so that has got no meaning, because writing to the memory we are not checking anything. So, for checking we need to have a read operation. So, my template must end with a read operation. So, that is the other one. So, this is an example. So, how this say we have started with a single write operation, write 0. So, this is a march test with whose length is 1 n. So, you have number of memory operations. So, if there is an n bit memory, then we are doing n memory operation. So, this has got one template of write operation. Now, when we are extending this W0 may be extended with W0 followed by R0. So, that is a read extension, or we can have one say this one. So, we can extend this by another write operation and then another read operation. So, this way we can have this we can generate this merge test from starting with the basic template to the successive ones. So, this is the complete one. So, it generates go on generating the templates, and after that there are this filtering operation that filters out the unnecessary sequences, and only the usable sequences will survive. So, this way we can generate a number of sequences, and then the time constraint being infinity. So, it will go on generating the test patterns until and unless all these faults are getting covered. So, it will go on generating the different test templates. So, it goes up to 11n. Okay. So, this is actually the coverage information, like if you have got this M11, that is a standalone write operation, it is not doing any test. So, naturally it cannot have any fault coverage. So, fault coverage is 0 for this. Then this M12, so this has got a fault coverage of this one, this stuck-at fault. Stuck-at fault coverage is there. So, it is detecting the stuck-at fault. Similarly, this is detecting this M13. So, it is detecting this much of stuck-at fault, and other faults are also there. So, different color bars are identifying. So, interestingly, as you are increasing the length of the test, okay, the number of operations, read write operations that you do, so more and more faults will get covered. So, when we come to this M111, so you see that is the number of read write operations 11. So, at that point all the faults are getting covered. Okay. So, all the faults are getting covered. So, you have reached the 100% coverage. So, we can stop at this point, our test generation process can stop at this point, provided these are the fault models that we have to cover. So, if we are looking for only say stuck-at fault, then we can stop at this point itself. So, M4 we can stop. So, only 4 length test sequence will be sufficient. So, this is the another fault coverage. So, if you take only a single test length, so if your test length is restricted to say 6n, so then what happens is that then also with 6n restrictions also there are several test sequences that can be generated by that tags procedure, and the list that we have seen previously. So, in that this M1, M2, M3, M4, so these are various 6 length sequence, and you see that all of them do not have the same level of coverage for all the faults. So, naturally we will like to have the those tests which will be covering most of the faults. So, accordingly you can select any of these patterns M1, M2. So, M1 is really poor because some of the faults are not covered and all that. So, it is not that good. So, whereas these are better. So, this way you can get some selection from the tests. Next, we will look into memory beast. So, basically what we have said is that, so there is a merge test sequence that we need to apply to the memory for testing it. But for how do you apply those test patterns? Are we applying from outside? So, if we are applying from outside, then we have to have all those controls. Okay. So, we have to access individual cells, and then we have to send individual patterns and all that. So, BEAST is a better option for memory testing, because this BEAST can be integrated with the memory itself, and once it is signaled to start testing, so it can go on doing that. It can generate the patterns as per the template, the read write requests, and it can check whether it is okay or not. So, ultimately it can result in a go no go solution telling whether the memory chip is okay or not. So, what are the issues in BEAST design? First of all, what are the functional faults to be covered? So, which faults you are going to cover? So, that is an important issue. So, there may be static or dynamic mode faults, there may be operation mode. So, what are the different operating mode that the RAM the memory has? What are the defects like open, short, timing parameter, voltage, current? So, what are the defects we are going to cover? Can it support fault location and redundancy repair? So, if it does it have the capability to locate the faulty location? Actually, what happens is that memory as far as the technology is concerned, so this is an array of same type of cells. So, if one cell is faulty, we can replace that cell by another one. So, my address decoder can be modified so that it refers to a different location when that particular address is generated. So, that way if I can do this thing, so if I can support this correction, this repair part, okay, and also this redundancy, because some of the array locations may be redundant because of this duplication. Does it support burn-in? So, actually this burn in is that when this design first comes into existence, so it is kept on for quite some time, and then if there is a problem, then many of the wrongly manufactured modules, so they will die down. Okay. So, that way our yield can be improved by removing this burn in pattern, burn in chips. So, this can it support this burn in detection, can it support on chip redundancy analysis and repair. So, that is also important. So, does it allow characterization test as well as mass production test. So, characterization test is that can check the memory thoroughly, or mass production test is those tests that does not do thorough check, but it is much faster than mass production test, though all faults may not be covered. So, does it allow both of them? Can it really replace ATE? So, ATE and the laser repair machine. So, this is actually the thing, like if we detect that there is a fault, so then many a times what is done is that by laser technology we can rectify some of those faults. Okay. So, that way there may be some laser repair machine, so that can take care of this faulty chips, and they can introduce some connections. So, if two lines are shorted, so it can put a laser beam there and remove the connection between them. So, like that it can do many operations. So, this ATE plus laser machine, so can it be avoided if I use a BEAST. So, the necessity is the programmability, speed, timing accuracy, threshold voltage, and the parallelism, all these things. So, when I am talking about a BEAST, so these are the questions to be answered, like which type of features will the BEAST provide. So, typical RAM based approaches are like this. So, there can be two different methodology or three different methodology. One is processor based BEAST. So, processor based BEAST, so they are programmable. So, there will be an underlying processor integrated with the memory, and it will be generating the pattern. So, since it is a processor, so you can program it to generate different types of patterns. So, that way it is good, because you can cover a number of different fault models. Then hardware BEAST. So, hardware BEAST will be faster than normal this processor based BEAST, because this software part is not there. So, it is fast and compact. And hybrid, a mix of these two, some part is hardware and some part remains in the processor. Then the interface, whether it is a serial scan or 1149.1, the boundary scan technology, or it is parallel. So, is there an embedded controller and or hierarchical structures like that. So, patterns, the march like patterns or pseudo random patterns or others. So, what are the different types of patterns that the RAM BEAST will generate. So, these are the different issues while we are discussing about RAM BEAST. So, this diagram shows a typical architecture of RAM BEAST. So, this is the RAM. So, that has got a test caller, basically some multiplexers, so that it can get the address and data lines from this RAM from the BEAST module, as well as it should get address and data lines from the processor for normal operation of the RAM. So, there naturally there will be some multiplexers that will be selecting between the two. So, there is a pattern generator. So, this pattern generator module, so this will be generating different march patterns. Okay. Or if it is a march based test, or if it is a pseudo random test, it will generate those pseudo random patterns like that. And there is a comparator. So, suppose I am generating a read 0, read 0 is the pattern that is given. So, this read 0 is coming to the comparator as well, and it is going to this cell. So, that particular location is read, and this value is available via comparator. So, comparator will check whether the value coming from the pattern generator is same as the value coming from the memory cell. If they are not same, then there is a problem. So, this location is faulty. So, fault is detected. So, that is why it generates a go no go type of signal. And if it is a write operation, of course, comparator does not have to do anything. So, the corresponding location will get written. So, corresponding to the read operations only, this comparator will check the value available from the pattern generator and the value available from the RAM to see whether they are correct, same or not. So, this is a typical RAM based architecture. So, this actually shows a DRAM structure. So, this is the memory array, it has got sense amplifiers and all that, and as we know that the memory is arranged in a 2D fashion. So, there will be a row decoder and a column decoder. So, the row decoder this has got 1024 rows, each of 256 columns. So, they will be generating any address that we have. So, this address has got a row address part and the column address part. Row address part will comes to the row decoder, column address part comes to the column decoder, and they are actually selecting a particular location. Now, if you want to write something, then these D lines, so they actually get the data 16-bit data lines. So, that is coming to the data in registers. Similarly, if you want to read something from the memory cell, then this 16-bit data is available through the Q line. So, normally these lines are coming from the processor, but in a memory based environment, so they can also come from the memory based. So, the test caller is not shown here explicitly, that will have the multiplexers at all these points. Okay. So, so this row address selector, column address selector and write enable. So, these are some timing controls that are given. So, when this row address is put into this line, then this row address selector is turned on. Similarly, this column address selector will turn on the column address, and this timing is also controlled by the refresh controller. So, since it is a DRAM, so it requires refresh. So, there is a refresh controller which also generates the address. Okay. So, that is there. So, we have got several sources of this address part, and accordingly it will be generating they need to be multiplexed, so that they can be applied to the RAM. So, this is the operation. So, initially this row address selection, when it is making a transition from high to low, the row address is provided at that time, that gets latched. Similarly, when the column address selection line makes a transition from high to low, this column gets selected. So, whenever this column address selection line is making a transition high to low, this corresponding column address is selected. Then this write enable signal is given. When this write enable signal is low, making a transition from high to low, then the D value is available. So, that will be written onto the RAM cell, and if it is just reading the value, then of course, when this write enable is high, once the addresses have been put, this value is available on the Q line. Many a times what happens is that this D and Q lines, though it is shown separately here, D and Q lines are shown separately, but they may be together. So, they are written as a DQ. So, this DQ is written like this, and this OE line, so output enable line. So, this will be when this makes a transition from low to high. So, at that time this Q value becomes available onto the bus. Okay. So, this way this DRAM operation takes place. So, it can read an entire page in this fashion by generating different column addresses. Okay. So, for all the columns for a particular row, it will generate the data. Now, for the BIST, as far as the BIST architecture is concerned, so this part is that EDO DRAM. So, this part is the BIST part. So, this has got several components in it, the BIST controller, decode logic, test mode selection. So, march. So, you see some of them like BIST scan paths are there, then burn in commands, march commands, diagnosis information. So, they are all going to the sequence controller, and the sequence controller accordingly is generating this row address counter, column address counter, control counter, timing generators and all that. So, that these addresses will be put onto this interface buffers, and they will go to the row address buffer, column address buffer, etc. Similarly, when the values are read, so they are coming to the comparator. So, comparator has got entry data available from the sequencer as well as this memory cell. So, they will be compared, and accordingly it will give a go no go type of signal. So, there are many more signals. So, I will not go into much detail because that itself is quite complex, but essentially what means is that the controller, so it is designed to provide all the read write instructions and these addresses to the memory for getting its content checked for faults and all that. So, to conclude, so BIST is the best solution for testing embedded memories, because the cost is low and it is effective and efficient. So, because if you are using ATE, then ATE for testing so many locations, so many memory locations, so it will take a lot of time. Then further improvement can be expected. So, we can have some timing or delay faults and disturb faults, so they can be covered. Built-in self design and built-in self repair, built-in self diagnosis BISD and built-in self repair. So, these are the two directions where works are going on. because diagnosis will diagnose the particular cell which is faulty, and repair will try to repair it in terms of maybe replacement and all that. Then this content accessible memories, so for them BEAST is a challenge, because the way they are accessed is different from this DRAM, and for a flash memory also they are different. So, accordingly we will have to have different type of BEAST technologies. Then BEAST, BISD, BISR compilers are to be there, because they, in that case they will get automatically introduced into the memory. Okay. So, if you say that okay, this memory should be BEASTed, then the BEAST will get introduced into the memory. Wafer level burn in and test, so that also has to be there. So, accordingly we will come to, once we know that these dyes are not good, so you can get some information about the known good dye, how many dyes are good in your entire wafer. So, that can be collected, and so that gives gives an indication about the quality of production. So, this memory testing, as far as algorithms are concerned, so it is dependent mostly on the merge sequence generation, and we have seen that unlike other test pattern generation algorithms ATPG, so here it is based on simulation. So, you can have your own test generation procedure. So, you can think about any way of generating these read write commands, and then you can take help of this simulator RAMSYS to generate to check whether the faults are getting covered properly or not, and accordingly you can get a confidence about the quality of the test generation algorithm that you are proposing. So, that is on the test generation side. On the test application side, we have got this BEAST. So, this BEAST can be used for generating this test pattern, applying these test patterns to the memory array. So, combining these two, we can get effective solutions for this memory testing.